Hi, good morning.
Hi, good morning, Miriam. Right, good morning. Today we look closer at regression. Please sign in.
Good morning.
Good morning, Fahima. Okay, so let's begin then. So I just want to quickly go through what we did yesterday, just to make it clear what we covered in terms of how we do a regression and how we can investigate the results a bit further. So that's what we looked at yesterday. We just had the simple relationship between temperature and the number of bicycle rentals. And then we went on to estimate what a trend line might be for that, how that could be calculated. We introduced the concept of f of x, which you shouldn't be worried about. It just means something you do with x to make it equal to y, which in this case is multiply your x by 1.7 and add 20. So that's how you get from your x to your y, multiply by 1.7 of your x and add 20. So that would be f of x equals 1.7x plus 20. That's how I would write that. So y equals f of x, which equals 1.7x plus 20. And then we looked at the idea of y hat, which is our predicted value based on our trend line. So y is our actual value. For our actual value of x, we can measure on our labeled sample an actual value of 156, and then we'll see what our trend line would predict for that actual value. And then we looked at the difference in several ways. We looked at the actual difference, the absolute difference. And of course, it doesn't make sense to add those up because positives can cancel out negatives and vice versa. So we look at the squared of the difference. That's good because it gets rid of the minus signs and at least you come up with a sensible number. And then quite often we look at the root mean squared. So that is the square root of the averages, sorry, the average of the squares rooted, so the square root of the mean of the squares, which is root mean squared, and we can then see how x and y compare as our plot. We've got our root mean squared error here, which we got calculated at 3.13, because our average or our mean squared error was 9.79. Square root that, 3.13. So what we're just saying is that our root mean square indicates that the loss is just over 3, which means you can interpret as meaning roughly that on average, incorrect predictions are wrong by around 3 rentals. Okay. So what we can say is if we predict 15, then the actual result can be somewhere between 12 and 18. That's what that means. The actual result is very, very likely to be somewhere between 12 and 18 if we predict 15. That's exactly what that means. And that's quite a reasonable type of prediction. And then we looked at R squared, which we talked about as being a correlation between x and y squared is produces a value between 0 and 1. So it can measure the kind of variance that you're getting. So how much the results vary. And it's very important if you're simplifying a model that you retain as much variance as possible, because you don't want to oversimplify your model and you won't be able to capture the variance in the data. Your model simply will miss it. And that's kind of underfitting, which we'll get on to next. So we trained and we introduced the terminology, and we trained and evaluated for our bike rentals. And we went all the way through this. And we trained our regression model for it. And then we looked at the idea of a training set and a test set. And the difference is the training set is used every single iteration of a training loop. The test set can be used once per training loop, but then if you're optimizing your training, you might use the test set more than once in that case. And if you use it too many times, it means that your model actually becomes your test, which is not good. And to counteract that, we did something else. And then we introduced this idea of that was in the next one. Yeah. I just want to be sure that okay, so this is as far we got, discover new regression models. Then the last thing that was introduced was the idea of a withholding validation set. So that's a few values that you keep back, that's not allowed involved in the training, definitely, not even allowed to be involved in the testing, but is used just once. When your model you think is finished and trained as best as you're going to train it, then you use these holdback values, samples, to check how well your model performs with those. And if you're lucky, your holdback samples are all well within your model's capability in terms of understanding the variance in the data. If you're unlucky, then those samples which have been taken randomly could easily be outside what your model has been overtrained to predict. And in that case, you will find that your root mean squared error of your predictions of your validation of your holdback samples is worse than your testing samples. Okay, so this is where we're going to start today. I'd like you to read this just for a few minutes, and then we'll talk about it. So far, we looked at fitting a straight line to some data points. However, a regression can fit many kinds of relationships, including those with multiple factors and those where the importance of one factor depends on another. And this is a kind of weighting. So where something is weighted, it means it's multiplied or modified in some way to reflect its importance. So there are many kinds of regression models, and one's chosen work because they work well with small data samples, are robust, easy to interpret, and a variety exist. So linear regression, that's the simplest form of regression with no limit to the number of features used. So we got on to the idea of yesterday of including more than one feature in our regression. And what happens there is that the regression algorithm looks at the relative importance. So in effect, it runs the model, takes that parameter away, and runs the model again. And if it doesn't have much of an effect, it's then simply weights that particular feature down as not being so important. And it does that for all of the features. And in fact, it can do it in combinations as well. So the idea is it can work out what's the most important feature. Obviously, if you've only got one feature, you've got one that you know and one you're trying to predict, it doesn't have any choice but to use that one feature and to use that to its full extent. But if you've got more than one feature that can affect your final outcome, your y value or your y hat value, your predicted value, then you have to work out what's important and what isn't. So decision trees are completely different. Decision trees are step by step for predicting a variable. So if we think of our bicycle example, so simply we're applying a set of rules in some kind of sequence. That's what a decision tree is. It says, is something greater than something else? Then it's that, and it will go down that branch of a tree. If it's less than something else, it might go down this branch of a tree. And by designing a tree of decisions, then you can get to one point or another. So there are many kinds of decision tree. In fact, they're often combined together to make forests. And a lot of these algorithms, modern machine learning algorithms, use forests of trees, and some even use forests of forests. And in fact, probably one of the best classifiers around are something called a random forest, which basically says, go at the data, just keep creating forests until one is a little bit more successful than another one, and then just keep along with that one. So that's a random forest kind of approach. And they're very powerful techniques, but I've not personally got in to use them, and I will. I've set aside a month of my research to look in detail into whether or not I can use a forest approach to my particular problem of 1,000 or so keywords across 1,000 or so questions. I might be able to set up some kind of decision tree process to partly classify or wholly classify my data set. So a step-by-step approach, predict a variable. We think of a bicycle rental decision tree. We must fit the examples between ones that are during spring and summer and autumn and winter. Make a prediction based on the day of the week, spring, summer. Monday may have bike rentals of that, while autumn, winter, Monday may have a rental rate of 20. So we can characterize our data set by asking the right questions about it. And more importantly, asking the right questions in the right sequence about it. So a very large number actually of the most effective systems overall, rather than just algorithms, use an ensemble algorithm. So construct not just one decision tree, but a large number of trees, allowing better predictions on more complex data. Example algorithms such as random forest are widely used in machine learning and science due to their strong prediction abilities. Yeah, random forests. Data scientists often experiment with using different models. In the following exercise, we'll experiment with different types of models and compare how they form on the same data. Now, the thing with models is it really is horses for courses. You really have to apply the right models for your data, not just in terms of the number of data or the number of features in your data or the number of samples that you've got, but how interrelated those samples are will help you decide what model to use. If you're sure all the features are completely orthogonal, meaning completely independent of each other, then you use a different algorithm than if you find that they're multimodal, that they can exist in more than one area. So let's start off experimenting with powerful regression models. I need a sandbox to start off with, so let's activate that. I've got 2 hours left in my sandbox. Do we all have a sandbox? Yes? Okay, so let's look at this. We're using pandas as always for our arrays. We're using linear models, so we're using linear regression from the sklearn package linear model sub package. We're going to import that. And then from the metrics, we're going to import mean squared error and R2 score. And from the selection functions available in sklearn, we are going to import train, test, and split. Okay, that's our model selection. And then obviously numpys is NP, and matplotlib as plot. So anything we do with plot is actually calling matplotlib, and we're going to use the inline version. So firstly, go get your data, and the bike data is to read it as a CSV file and take the column day is, well, date time index, that is going to be that is a specialist function for extracting dates, basically. And our numeric features we're going to define as this list. temp, atemp, hump, and wind speed. So they're the kind of columns we're going to look at. And our categorical features are season, month, holiday, weekday. So we're telling here, we're making the distinction between features that come out to be numbers and features that come out to be categorical values. So for our weekday, we decided whether it was 1 or 0 and so on. So mostly, and with the weather situation, we did a one-hot encoding of it from 1 to 6. And season, again, that would have been a one-hot encoding eventually of 1 to 4. Month 1 to 12 and so on. We looked at actually the graph of those things, the bar graph of those things yesterday to see that we had 4 seasons, 12 months, 2 true false whether it was holiday, true false whether it was weekday, weekday 1 to 5 and working day true or false, weather situation and the day. So, and the bike data is the numeric features plus the rentals, and we're going to do a dot describe of that. So we should be able to see that. Let's have a look at our bike data. So we've grabbed in dot describe of our bike data. So we should get a nice breakdown in terms of mean, medians, min, max values, and all that kind of stuff. And separate the features and the labels. So XY bike data for all of these, and then we're going to train them. So we've got X train sequence. So that's this is where we do our split. We do our train test split here, and we end up with 2 sets, X train and X test, and then we print them. So that's what we should do there, just see what happens. So we now got X train, X test, Y train, and Y test. And we'll end up with pretty much what we thought, which is we're going to end up with our so this is our Panda array index here. Oh, I see. This is all one row. Should be connected together. So this and this should be connected together. That makes more sense. Okay, we've got training set 511, test set 220, which is what we kind of expect. So let's try the different algorithms now. Now that we've created our test and training set. The linear regression algorithm we used last time to train the model with some predictive capability, but there are many kinds of regression algorithm we could try instead. As we said before, linear ones taken in kind of more than one variable. So let's look at these. Linear regression we used above, which is technically an ordinary least squares algorithm, but other variants such as lasso and ridge, they are actually called that, ridge regression and lasso regression. And they work exactly the way you think they might based on the description. So let's see if we talk about it. So there's a full list here of scikit-learn estimators that encapsulate algorithms for supervised machine learning. So you can just look at the documentation when you've got some time and have a look at that. It's always good to look at the documentation from the actual company, organization that's producing it, rather than some blog that someone's done, because I spend a lot of time doing that, going to the wrong places for information, and it can cost you a lot of time. So we're going to experiment now with our first linear algorithm. So we're going to try lasso. So let's have a look at lasso before we do anything else. So if we just type in here lasso regression, we'll get a little bit of an explanation. It's a type of linear regression that uses shrinkage. Shrinkage is where data values are shrunk towards a central point, like the mean. The lasso procedure encourages simple, sparse models, i.e. models with fewer parameters. The acronym LASSO stands for Least Absolute Shrinkage and Selection Operator. Okay. Yes. I want to get a better description on it than that, actually. See what Wikipedia says. What do you mean scroll away? I can't scroll away. Block the... Okay. Machine learning lasso is a regression analysis method that performs both variable selection and regularization in order to enhance the prediction accuracy, interpretability of the resulting statistical model. It was initially introduced in geophysics and later by Tibshirani, who coined the term. A simple case reveals a substantial amount about the estimator. These include a relationship to ridge. We can talk about ridge regression in a moment. No, I want a better explanation of it than that. So we can find it's used over regression methods for a more accurate prediction, yes. Uses a shrinkage where the data values are shrunk towards a central point as the mean. Okay. So what that can do is to brings in outliers, makes them less significant. Here we go. Try that one. Complete understanding of lasso regression. So if we can get a summary. Again, I don't normally trust blogs, but sometimes they get a good insight. That's a good question. Linear regression is the most basic form where the model is not penalized for its choice of weights at all. Lasso is a modification of linear regression where the model is penalized for the sum of the absolute values of the weights. Now, what do we mean by penalized? What it means is that we will punish the model if it includes values that are a long way away. Because if they do that, those can they can drag the center away from the other values. So what you want to do is to put in a lot of algorithms use something called a long tail, where it stops, it pulls in those values. It gives them less significance, basically. At the moment, the significance of a value away from the mean is not itself is not weighted. But with the lasso, then that's what's actually happening. And you often do that. T-SNE, for example, is one of the most recent kind of clustering algorithms, and that works particularly well because it does have a long tail. It prevents all of the samples being put together at an edge, at a boundary. when it comes to clustering. So it kind of redistributes them, but the problem is sometimes it doesn't know quite what to do. And as Dr. Rice says, it doesn't know whether to pick up a putter or a driver sometimes, and you can see some strange results. Let's try this one. Might give us a quick difference here. Oh no, you've got to read the history again. You've got to pay some money for that, so that's no good. Come on, I want somebody to give me a very simple tutorial. I don't really want a complete tutorial. Don't want a comprehensive guides. There we go. Let's have a look. That's not what it says on the there we go. That's what I want. Oh, it's that story. Oh, come on, we must try and do better than that. There's another one you have to sign up to. Let's go down. Oh no, it's good. So let's read this. OLS, which is what we're looking at, is one of the oldest and most simple algorithms used for regression. That's what we're doing right now. However, there are now several variants that were invented to address some of the weaknesses when we're using regular least squared regression. So these are our improvements. Despite being one of the oldest algorithms, linear models are still very useful. In fact, they outperform fancy and sophisticated models. They're particularly useful when there is not a large amount of observations, as in our case, or when the inputs reliably predict the response, low signal to noise ratio. So what that means is that all of the values, all of the features are important. And you can't say of equal importance, but are important. This idea of signal to noise ratio is an engineering term, and it's all about the ratio between the things that are indicative, the things that you want to see, divided by the all of the sum of all of the things that don't give you any information that you don't want to see, the so-called noise. Okay, and the quality of many systems is often decided by their signal to noise ratio, how good they are. For example, an amplifier give you a signal to noise ratio of a certain number, and that number will tell you how good it is at filtering out or not amplifying the noise as much as the signal. So, and that's what we're talking about here. So it's an interesting concept, the idea of applying signal to noise ratio concept to machine learning. In this article, we'll first review the basic formulation of regression using linear regression, discuss how we solve for the parameters using gradient descent, which is like we thought, and then they're going to look at ridge regression, which we're going to look at next, and then discuss the lasso, and finally the elastic net. So we're going to look firstly here on this one for regression, then we're going to move on into lasso, and then we'll go back to our course for ridge regression and elastic net as well. Okay, so don't really want to see it with his data set. I'm more interested in so this is the mathematical basis of your regression, which you certainly don't need to know. Don't need to know that. Then we get from that we get our cost functions, and we can plot that in a 3D world here. Don't worry about the maths. So linear regression. Most simple regression algorithm was first described in 1875. The name regression derives from the phenomena Francis Galton noticed of regression towards the mean, which is what's actually happening here. This referred to the fact while children of very tall parents or very short parents were usually still taller or shorter, they tended to be closer to the mean higher. This term was termed regression towards the mean. That's what we do. Don't worry about the maths. All that's doing is working out the individual, the least squared model here. And then we did gradient descent, but this is explaining how it works from scratch. What we're looking here is ridge regression. Oh, that's what we're doing next. So I don't think we're going to go through that in that way. I think we're going to go back to this and see if we can work out what the lasso does for us. So we're going back to the main section again, and we get to see the lasso algorithm. I don't think we get to see the inside of it. No, because the lasso is a built-in function, so we don't get to see under the bonnet. If we wanted to, then we could look at this here, but that's not at our course level at the moment. I'm sure we'll all get onto that eventually, but this is simply printing our mean squared error, our root mean squared error, and our R2 value. Remember, the closer to 1 the R2 value is, the better. Okay, and that's not bad. That is not bad based on a lasso regression. You see how it tends to bring them in because it punishes ones that are further away. So it kind of compensates for them. And then we're going to look at a decision tree. So an alternative to a linear model. Morning, Richard, didn't see you there. So we're using a tree-based approach, which the features are examined in a series of evaluations, each of which results in a branch in the decision tree based on the feature value. At the end of each series or branches are leaf nodes with a predicted label value based on the feature value. So the idea is that it's not actually a tree, it's an upside down tree. So the leaves are at the bottom and they give you your results effectively when you get to the final leaf of the tree. And there could be many branches. So again, unfortunately, it's pulled in decision tree regressor, and we've got to fit them with the train values. So it's pretty straightforward to use. Following it step by step under the bonnet is something we can't do in this course, but it's fascinating the way it decides which rules to make and when to apply them. But unfortunately, that's hidden inside here. But we can look at the results, and you just simply have to export the text and print the tree. So the tree is export text of the model. The model is here. So the applying the decision tree regression with a fit instruction using the X train and the Y train data will produce a model which is printable. You can print that model, and you do it by calling the export text function inside them, which is a feature, an attribute of the model, and then we can just print it. So this is what we get. Quite fascinating. This is our decision tree regressor. Imagine it's upside down. It's at 90 degrees. Sorry, not upside down. Imagine it's 90 degrees. and it looks more like an upside down tree. So we start off with, these are the features, and it's asking the question here all of the time. So the first branch of the tree is feature 6 less than or equal to 0.45, then 0.50, 0.32, 0.41. What's happened is, if you think about it, it's trying to find a limit for the feature. So feature 6, feature 4, feature 7, feature 8, asking questions firstly about each of the features as to what values there are. And then, going further down the model, yeah, you get to the bottom. Yes, that's right. The final value is here for each of the features. And so it's just asking questions. And obviously all the features are the ones that were listed in our model. Quite a powerful idea. And it's, yeah, basically it's trying to come up with rules that can break down the set. And if you can break down if you can sum up a set of rules that enables you to break down the entire set and get to any member of the set by following the rules, then that's a complete model. But let's see. So let's move on. So now we have a tree-based model, but is it any good? So we're going to evaluate it with our test data. So here we go, mean squared error. So we're going to measure our mean squared error using our test data based on the predictions. And the predictions comes from our previously described model of predictions on the X-test. So we're applying X-test. We're taking our model, which we've got, and we're applying the predict attribute to the test vector that we've kept back. And that will produce a set of predictions. And then we can find the mean square error between the Y-test values, which are the real values that we held back, against the predictions for the Y. So that's Y against Y hat. So we should then get the mean squared error between those two and then print it out, and then the square root of that, of course, and the R2 score, which again comes straight from the predictions. And then predicted versus actual. Well, I'm not going to explain that, but it's just a nice little XYZ plot. Let's see what we see. It'll give you a picture of how good it is. So we've got our mean squared error, our root mean squared error. Our R2 is slightly worse, isn't it? But look at this. It's really brought in these and thrown away those. It's basically saying, I'm not going to take any notice of you. I'm going to punish you badly because I don't think you're going to have an effect. I'm not going to drag this line towards you because you're a long way away. And that's what all this is about. By making the tendency of it to weight strongly the ones that are closest to the line. You then don't allow this to be deflected by noise, these values here. And again, you can be sure that these, with our model, don't have any much of an effect. They're not what we might call representative. So that's better, definitely better. We've got 486. What do we have before? Slightly more. Is it better or worse? 448 before. So it's slightly worse, isn't it? In terms of our root mean square. Let's see why. Yeah, it's chucked a lot of them away, isn't it? It's chucked a lot of them away. And of course, this now has got a big error in terms of where the data is to our line. Because that shouldn't have, yeah, it shouldn't have changed. The actual position of our data. Yeah. Yeah, but yeah, because the R2 is looking at the variation around the mean, and there's very little variation around the mean for most of the data. There is a huge variation around the mean for a small amount of the data. So overall, the R2 is quite good because of this. See, it's better than what we had here because there's a lot of this, and here there's almost none of it. I mean, let's face it, if something's on the line, it's on the line. It doesn't matter what the model is, it fits. And so the errors are only really all about the ones that are way off the line. They dominate that. And there are other techniques to use. So the tree-based model doesn't seem to have improved over the linear. So what else could we try? On ensemble algorithms work by combining multiple base estimates to produce an optimal model, either by applying an aggregate function to a collection or a base model, sometimes referred to as bagging, or building a sequence of models that build on another to improve prediction performance, referred to as boosting. So bagging and boosting is an interesting and well-researched area. And what it's saying is that you can, if you've got if you can propose several models that are close to each other, but actually gather more information in for you, gather more, more representative than the samples, then what you do is combine those models together as a single model. And that enables you to, if you like, get one model to grab those bits, one model that's really good on those bits, and one model that's really good on those bits. Okay, that's bagging. Alternatively, if you find that the data is really distributed, what you can do is to create new, so run two models at the same time to deal with the different areas. Okay, and that's boosting. So you will improve it. So you build one upon another one. So you're extending out. So one is kind of compressing the models, and the other one is expanding the models. It's about so bagging and boosting. Let's try a random forest model which applies an averaging function to multiple decision tree models for a better overall model. So let's have a look at this. So we've got our random forest regression as before. Fit X train, Y train. Evaluate the model. I'm just looking for the difference here. Let's have a look at what we did before. We had here, the model was, that was a decision tree regressor. And now we're looking at a random forest regressor. Now, random forests are moving towards the most effective classification systems. And the boss of our entire department, Professor Gaber, who's in Egypt at the moment, is a big fan. If you read any papers, let's try it. Let's try our random forest regressor. See what we get. So basically what that's doing is, it seems strange to do it this way, because it kind of, to me, I always thought this is overfitting slightly, because what we're doing here is creating our model ensemble to to get the lowest error in the final prediction. Now, that it is not something that's got a tendency to overfit, then you can imagine that is, because it's going to try and create not just one model, but lots of models, and between them get a really good mean squared error. So it's so important to have a holdback set in that situation. Let's see what we've got here. So with our random forest regressor, we've got our mean squared error is down to 344, and our R2 is now 0.76. So what we've done is we've used different models for different parts of the data set. And so we've remapped our real data points to reflect this ensemble of models. And that's given us the best results so far, isn't it? For good measure, let's all try boosting ensemble algorithm. We'll use gradient descent to estimate which, like a random forest algorithm, builds multiple trees, but instead of building them all independently and taking the average, this tree is built on the outputs of the previous one in an attempt to incrementally reduce the loss. Okay. So this is the boosting algorithm then. When we're taking what's good, what's working, and building our next level, not just randomly as a selection, but based on what is currently doing well for us. And that is using gradient boosting, a regressor, same idea, and we'll see what the results are for that. I can assure you the maths for this is horrendous. So don't go anywhere near that. But getting an understanding of what bagging and boosting is. Let's have a look, see our results. How are we doing? Now look at that. We've now got it down to 322 and our R2 is 0.79. So random forests with gradient bagging and gradient boosting has given us our best results so far. And you can see how it's brought in those outliers. It's remapped them so that the error is much lower. It's not really made much of a difference to the gradient as such, because otherwise all those values, see the gradient's pretty much the same, but it's brought in a lot of these values now. See, they're a lot denser. These around here have been really brought in. Okay, so we've tried a number of new regression algorithms to improve performance, and our notebook will look at tuning these algorithms to improve them even further. So let's execute ourselves. See what we've actually done. Well, I think that's a dummy end to the code book.
Yeah, that's strange.
Yeah. Very odd, isn't it?
Yeah.
Next, improve the models with hyperparameters. Now, I hate these. So these are parameters that that control the model that often don't arise from the data. You put them in first as a kind of estimated value, and unfortunately, with a lot of algorithms, the outcome depends upon your choice of hyperparameters, and it's not good. That shouldn't be the case. It should always, in my personal view, the results should always be the same. If it's based on real data and you're making real predictions and you want to minimize the error against real labels, then it's just my view. But let's see. So have a read of that.
Steve, you're on mute.
Keep doing that. So simple models, as we know, can be fit with a single step, while larger data sets and more complex models must be fit by repeatedly using the model with the training data. Be very careful with that. And comparing the output data with the expected label. If the prediction is accurate enough, we can consider the model trained. If it's not, we adjust the model slightly and loop again. That's a simple approach to how we could train something. However, hyperparameters are values that change the way the model is fit. So, for example, the learning rate is a hyperparameter. It sets how much the model is adjusted. When it's applied to a gradient descent, the hypermodel might just simply say how big a step you take in one direction or the other as you're training the model. And if you make that step too big, then you'll never get to the bottom value. You'll be unstable. It will just go side to side continuously and never reach the minimum. But if you have it too small, then it can take years to train. So you kind of need different techniques for that. Pre-processing refers to the changes you make to your data. Well, we've looked at that. We looked at cleaning the data set. Yeah. The one-hot encoding idea for categories. That's an important part of scaling features, which we've looked at. I think we're okay. And obviously setting the values so that they occur between 0 and 1. That's another one we've done. There you go. So for scaling both numbers to between 0 and 1 allows models to learn more effectively from the data, because you can have the same parameter then applying to both features, current feature values, and they'll have the same effect. Whereas it gets very complicated if they're not. Let's move on then. Optimizing and saving our models. Let's do that. So my sandbox is still activated. Let's go down a bit. So what we're doing here is we are loading our data again, setting the categorical features as before, grabbing that from describe, and we've separated the features and the labels, split the data into 70/30, and we're ready to run. So nothing's changed so far. We've just got our results for our linear regression and the training set, the data set being set to those values. So we now have X train, Y train, X test, and Y test. And now we're going to use a new function, gradient boosting regressor and random forest regressor. So we already have the lasso in there. Fit a lasso model on the training set, gradient boost regressor. Evaluate the model using the test data, which we know how to do, and plot the results. So we're ready to train the model by fitting a boosting ensemble algorithm. We call that a gradient boosting estimator is like a random forest algorithm, but instead of building them all trees independently and taking the average result, each tree is built on the outputs of the previous one in an attempt to incrementally reduce the loss error. Okay. Run that. And we end up with this, which is kind of what we had before. But the gradient boosting has done what for us? Well, at the moment, we haven't optimized our hyperparameters, so it's looking very much like the last plot that we did. Now, in the gradient boosting regressor, estimated definition in the output above, and notice that like the other estimators we tried previously, it includes a large number of parameters that control the way the model is trained. Let's find those. Nope, it's below then, isn't it? Yeah, okay, so these are the parameters here. The specific hyperparameters for an estimator vary based on the algorithm that the estimator encapsulates. In the case of the gradient boosting regressor, the algorithm is an ensemble that combines multiple decision trees to create an overall predictive model. And you can learn about those parameters. We won't go into the details of each one here, but let's find them. These are the parameters. Find the best hyperparameter combinations to optimize the R2 metric. So score is make scorer R2 score. So we're going to simply work out the best parameters that's going to optimize for R2. So grid search, and these are the parameters. So the best parameter combination is what's going to come out. It's going to be printed out for us. And then from that model, we can put in and get the best estimator and evaluate the model using our test data as before, and then plot the results. So these are optimizing the hyperparameters. Again, the idea of using the data to. So we now got 322. Well, that's not huge. The use of the random values in the gradient boosting algorithm results in slightly different metrics. In this case, the best model produced by the hyperparameter tuning is unlikely to be significantly better than the one trained with the default parameter values, but it's still useful to know about the hyperparameter tuning technique. Now, one hyperparameter for k-means is the value of k. And the technique for selecting the value of k is to plot the value of k against the error that you're currently getting for all of your clusters. And then suddenly, if it drops at a certain point as you're going through k, it means if the error suddenly drops, it means you've suddenly got the right amount of holes to put your data in. And so you want to detect this point, this so-called elbow point, of where the rate of the errors suddenly falls. So it means that you're at the first step towards final optimization. Of course, you don't want to go all the way, because in order to get zero error, you need to have one feature in every cluster, which is nonsense. But we know it's some number, and that number k. So that's a hyperparameter, and that method I just showed you there is the standard way of getting the value, or one of the standard ways of getting k. And it's like this here. This grid search program here will find the optimum values for the model, the optimum parameter values. And let's run it. And we run that. Where's our nice picture then? Ah, here it is. Yeah. So the use of random values in the gradient boosting algorithm results in slightly different metrics each time. Yes, we don't like that. In this case, the best model produced by the hyperparameter tuning is unlikely to be significantly better. Yeah, I hate that idea that your results are different each time. It's not good. We train a model with data that was loaded straight from a source file with only moderately successful results. I guess the alternative of not having random is that whatever values you're choosing are in fact biased in some way. By choosing a random value, then yeah, I don't know. I might use, instead of a random value, I might say, yeah, we've seen this data set before. It's absolutely identical from the previous runs we've done. We're going to start our hyperparameters as an average of all of the ones that it's ever seen. All the ones this data set has ever seen. I put an identity on it. And so if ever I see that data set again, I bring up the history of all its parameter values and I set it to the average of those, rather than set it randomly. Because then it's not really biasing, that's kind of zooming in into an area. The idea of starting from random each time, it's not good. You get quite a significant variation in the outputs. So that's what I think about it. So we train a model with data that was loaded straight from a source file with only moderately successful results. In practice, it's common to perform some pre-processing. Yeah, we do that. For the algorithm to fit a model to it. There's a huge range of pre-processing transformations that we know about already you can perform to get your data ready, but we'll limit ourselves to a few common techniques. So scaling our numeric features, normalizing the features so that they're on the same scale. Yeah, we did that. So really what we're representing in here is not a number, but a percentage of the maximum. That's the way, and then you can compare that. You are then comparing apples with apples. Normalizing these features to the same scale results in the following values. Assuming A goes from 0 to 10 and 0 to 1000 and C values from 0 to 100, you end up with the relative scaling here. is the same. So there are multiple ways you can scale numeric data, such as calculating the minimum and maximum values for each column and assigning a proportional value between 0 and 1 and using the mean standard deviations. So how well they are distributed around the mean, for example. Encoding them with variables. So this is, it works best with numeric features. So we've got that. So we encode it as that. Another technique is one-hot encoding, according to creating individual binary 0, 1 features for each possible category value. For example, you could use one-hot encoding to translate the possible categories into a binary column like this. So these are the possibilities, and these are mutually exclusive, and you just simply use the binary code to say which one a particular size is. To apply these transformations to our bike model, we'll make use of a scikit-learn feature called pipelines. And we know a lot about pipelines because we put those together during the designer. They end up with an algorithm. We'll fit the entire pipeline to the data, so the model encapsulates all the pre-processing steps as well as the regression algorithm. This is useful because when we want a model to predict values from new data, we never want to apply the same transformation again, and distributions and category encoding is used with the training data. So we can, by using a pipeline, a lot of these parameters keep their values and we can reuse them. Including the term pipeline is used extensively in machine learning, yes. It means very different things. In this context, we're using it to refer to a pipeline of objects in scikit-learn, but may have used it elsewhere to mean something else. Yeah, pipeline often means a sequence of processes, something to go through. And we are going to get into this after the break. So we'll come back in 20 minutes and look to see how sklearn does pipelines. See you then.
See you.
Okay, so we're back. So we're looking into a whole new world now from sklearn of pipelines and the particular way they transform the data prior to creating the model. So let's have a look at this. So we're going to, from sklearn compose, we're going to import our column transformer, and we're going to import a pipeline and a simple imputer and standard scalars, one-hot encoders, and obviously our linear regression model, and we're using numpys. Define the pre-processing for numeric columns, so scale them. So these are our numeric features in 6, 7, 8, and 9. We're going to do standard scaling using the numeric transformer. And the pre-processing for our categorical values, we're going to encode them using our one-hot encoder. Okay. And then we're going to combine them together to make our overall transforms, just to add them all together. And then we're going to create this pre-processing pipeline, and we're going to use gradient boosting regressor. Look at the number of parameters available for that. There's a lot of parameters there, isn't there? And it did an additive model in a forward stage-wise fashion. It allows for the optimization of arbitrary differentiable loss functions in each stage of a regression tree. Is fit onto the negative gradient of the given loss function. So basically, it's added to the one that's doing best. Fit the pipeline to train a linear regression model on the training set. Same sort of game. And we get our model, and let's have a look at it. And that will just simply tell us our 60, 70, 30 business. Let's have a quick look then. We'll end up with, this is our pipeline. So this is the model. This is what we're printing here. Tells what we're doing. So these are numerical places. And this is what's been applied. And these are the categorical places. That's what's been applied. And this is the one-hot encoder section. That's what's been applied. And finally, we're saying which regression is going to be applied. So that's our model. So it's trained up, including our pre-processing steps. And let's see how it performs with the test data. Let's have a look. Here's our, as before, our set of predictions for our y values is our model.predict of our test values from the xy's, from the x set. This is exactly the same as we did before, that the models is produced, the prediction is produced by applying the model.predict onto the test set. And our metrics then are obviously the mean squared error of our actual y-test numbers against the predicted y-test numbers. Sorry, the predicted, numbers for y-test. So So this is a prediction of the Y values from the X test values. So there are actually Y values being predicted, but they're from the X test values. So we apply the X test values and we get out our mean squared error based on the difference between the actual Y test values here and our predicted Y test values as before. And then we'll scatter it out and have a look, see what we see. There we go. So that's looking good. This is lowish. That's getting high. And it's looking nice, actually, in terms of the way it's bringing in those outliers there. Yeah. Of course, this bringing in mustn't be too aggressive. So the pipeline is composed of the transformations and the algorithm used to train the model. Try an alternative algorithm, we could just change that step. And that's what a pipeline is. The pipeline enables you to change any number of the steps and still maintain pipeline, mostly because we're all operating on the same bits of fixed data and reusing any predictions or parameters that have been optimized, we can reuse elsewhere in the pipeline. So again, using a different estimator this time, we're using a random forest regressor. What did we have before? Sorry, there's our pipeline. No, it's this one here, isn't it? Yeah, gradient boosting regression, you're absolutely right. So we use the gradient boosting regression, and this time we're going to be using a random forest regressor here. So that's the difference. But all the rest is pretty much the same. Prints our model as before and comes up with our results 324795. So we've now seen a number of common techniques used to train predictive models for regression. In a real project, you'd likely try a few more algorithms, hyperparameters and pre-processed train transform motions. It really is more of an art than a science in some respects. You really have to understand what your data set is doing before trying different models. And then we can see how we can use our trained model, import and save the model as a pickle file. So this entire thing now can get what we just had printed out there. We can save that as a pickle file. And we can reload it whenever we need it. That's our model using joblib. So we saved it here. Let's go back. I have to run that anyway. So let's save the model. So joblib.dump basically puts the model into that file name. And the file name is bikeshare.pickle. And now we can reload it straight away. So and we're going to create a numpy array containing new observation, for example. So we're just going to make this up. This is a made up number. A made up, basically it's a new row. We've made up a new row. And there it is. And our new sample is a format list X new. So that's putting it into a list format. and we use the model to predict tomorrow's rentals. So this is would have been one extra row. And we're going to say for that row of information, let's predict our rentals. So we've got our loaded model. There it is. We're making a prediction of it. Again, we're passing a parameter there. So we need to look at that. And we'll now get our sample and our prediction. So new sample, there it is. So what happens here where it says print new sample, we've just formatted it as a list of X new. So we've taken this, we've turned it into a numpy array, and then formatted it as a list so that we can just print it out like that. That's our list. And our prediction is 100 bike rentals. Sorry? 96. Yeah, you see, it's rubbish, isn't it? Just yeah. Did everyone get anything different from 100? Anybody there? Did you get anything different from 100?
Mine is 100 as well.
Ah, okay. Stamina got
Same.
96.
Yeah, me too.
You got 100. Okay. So yeah, it can happen. Depends what the values. Whenever you start off with a random, you'll end up with different numbers. I mean, that's quite a difference, isn't it? For exactly the same data. But that is probably within our RMSE error. What's our RMSE error? Let's print that, shall we? If we can get that. Prediction. And let's try and, hang on, let's have a look before we do summary. So we're applying it now to a lot of samples. These are new samples. And let's see what we get. So 5-day rental predictions. Doesn't really help us, to be honest, because it didn't say these are just extra ones. But basically, you can put in this information as your new row. It's now put in 5 new rows. And it's using that to predict what you would get. And these are the rentals that you would get based on this data. But it's interesting. Let's see if when we run this, we get different mean squared errors. So how do we go back? We're going to modify this to also print this to print the mean squared error to see whether our bike rentals is within that range. So what we want is the true value and the mean squared error. So there we go, there's one there. So we can grab here. Oops. Just grab that lot. And paste that down here. In here. Let's make sure we're using the same terms. Test, predictions, predict, dot predict. Yeah, we don't have predictions here, do we? We have result. So we have to put in here result, I think. Let's see if this works. Might have to do something else. Value error, print predictions, rentals format. No, it doesn't have That didn't work because we used it at the wrong place. So let's go back to here and use predictions. Predictions. And what we need is to get predictions from where we borrowed it. Results. Got predictions from here. So we need that as well. Let's go back. So we've got our value there. So I need to put that in here. Does X test mean I've got X new? Y test. Model. Got the model. Let's see if that, I might have to define what X test is, but let's see. Nope, there it is. So there's our new sample. The prediction is 100. That's wrong. Mean squared error is 324. That is not good with an R2 value. So I think my mean squared error is being applied to everything. What I want is the, yeah, this is the sum of all of them, isn't it? I want it on my value, just my value. So I don't want MSE. MSE is mean squared error of Y test and predictions. So I need not Y test, but I need mean squared error between Y test and the predictions for Y. That's for all of the values though, don't I? So I want to basically no, that's not my own value, is it? That's the sum of all of them. So if I wanted to find the mean squared error between Y test, I'd need to put that between Y test and I guess I'd need to divide that, wouldn't I? But it's meant to be the mean squared error. How can we get around this? What's these numbers? No, they're quite large. Nope, I don't think we can do that directly without scaling it again. Well, that's a shame. That's probably why they didn't do it. So they've got the 5-day rental predictions. There they are. Okay, so that includes the notebooks for the module on regression. We ran complex regression, tuned it, saved it as a model using Pickle, using joblib in a Pickle format, and used it to predict outcomes for the future. Okay, let's have a quick look at the knowledge check then. And we'll get on to something new. Answer the following questions to check your learning. You're using scikit-learn to train a regression model from a database of a data set of sales data. You want to be able to evaluate the model to ensure it will predict accurately with new data. What should you do? Use all of the data to train the model and use all of the data to evaluate it. Train the module only using the feature columns and then evaluate it using only the label columns. That doesn't quite make sense. And use it and evaluate it. Yep. Split the data randomly into 2 subsets. Use one subset to train and the other to evaluate it. I think we're probably going to go for 3, aren't we? You have created a model Object using scikit-learn linear regression class. What should you do to train the model? Call the predict method of the model object, specifying the training feature and the label arrays. Call the fit method of the model, specifying the training feature and label arrays. This is for training, remember. Call the score model, specifying the training feature and the arrays. So what we're going to do, we want to train a model. Are we going to use predict, fit, or score?
The second one.
Yeah, fit. Yep. When you fit data to a model, what you're doing is training the model. Okay. When you're predicting, you use that afterwards in order to predict for your input information, your test information, the ones that you've held back from your train, what the prediction would be for those. And then you lastly use your score method to compare what you predicted with what actually is the values. So Y test are the actual values and Y hat the predicted values. And so that's the order you would use it. If you train a regression model using scikit-learn, when you evaluate it with test data, you determine that the model achieves an R-square metric of 0.95. What does it tell you about the model? The model explains most of the variance between the predicted and actual values. The model is 95% accurate. And overall, on average, predictions are 95% higher than the actual values. Well, what do we think?
Is it 95% accurate?
Interesting idea. I think it might be about R squared is all about variation from the mean. So I think that might be possibly talking about the variance rather than the accuracy. But let's see. Let's put in variance and see if we're wrong. Yeah, so the R squared metric really explains how well your model can understand the data and how it varies around the mean value. That's okay then. So let's move on gently. There's our summary. So in this model, we learned how regression can be used to create a machine learning model that predicts numeric values. You then use scikit-learn frameworks in Python to train and evaluate various regression models. While scikit-learn is a popular framework for writing code to train regression models, you can also create machine learning solutions for regression using the graphical tools of the Azure Machine Learning. You can learn more about no-code development regression models using which we've done before. Create a regression model in Azure Machine Designer. We've done that before. Think you're ready to create your own regression model? Yeah, bring it on. Right. Try the challenge of predicting real estate property prices for the O2 Real Estate Regression Challenge notebook. Time to complete this optional challenge is not included in the optional time for this module, so you can spend as much or as little time on it as you wish. So let's have a look at it. Regression challenge. Run the following cell to load the data and view the first few rows. How do we run the cell then? Is it Control Enter? I don't think this is a real.
Could it be like the sandbox gone or not?
Sandbox gone. Yeah, maybe we don't have a sandbox for this.
Okay.
What we have to do is to run this in our own Python notebook. Okay, so what we might do, let's have a look at it. It might be a nice exercise. Okay, so we're going to put our coding in here. I don't think we're going to do this today. We might come back to it. So, go back to where we were, which is in summary here. And
Steve, was it GitHub? It could be that it's GitHub. I thought it's.
yeah, it was a GitHub. We could have just imported it in.
Yeah.
And that might have worked. But okay, let's get back to that. So explore other modules. Well, we know what our modules are. We just need to go back for the next module. Yeah, no, yes, unlock the achievement. Why not? Let's do that. Okay, so we're going to go back and take where we were. So that was all about regression, wasn't it? Modules. So let's go back to this. So this was our here. And then we started here. Let's see how far we've got. We got as far as train and understand regression models in machine learning, refine and test, train and evaluate, understand. I think we are here. Yes, I'll put it in the chat. That's where we are at the moment. It makes sense because all of the other achievement points are green and this one is not yet green. So it's going to be that. I'll put it in the chat. And then we're going to be looking at classification models. We looked at regression models. And now we'll look at classification models. So the link is here. If we can all get to that. I'll give you a minute to get to that.
Steve, you are on mute again.
No, try to mount the wall. Right, sorry, yes, we're looking at this module. Look at what are classification modules. Build a simple logistic regression model, which is exactly the same as we used in the studio and in the designer. Assessing a classification model. Well, we kind of did that, didn't we? We looked at F1 score and all of those things. That's what we'll be coming back to. Recall, precision, all those little parameters we started to learn about. those little metrics we started to learn about. We'll know about them in a more comprehensive way. We're doing that. And then we'll assess our particular logistic regression model, and then look at which other models we could apply and improving those as well. And then finally a knowledge check. So improving the classification model will be an interesting one. So let's begin. Read that for 2 minutes, please. And we're back to our dogs again. No, this is avalanches with ski slopes. Now, you're a dog person, really. I'm a cat person, I think. No, this is all about avalanches. Interestingly, in Canada, I was driving over the Rockies in the summer, because you can't really do it in the winter, and I stopped at the highest point to look out over the mountains in front of me, going right the way into the distance, and I noticed a concrete circle just where I was having my picnic, a big concrete circle, and then there was a plaque, something to read next to it, and they say this is where in the winter the Canadian Army, as is, put a howitzer, a cannon, and they fire shells up to 5 miles into the different mountain areas to cause avalanches, so that it's done in a controlled way. I mean, I just love to have seen it, because it was a summer's day when I was there, and it was lovely. There was some kind of gopher after my lunch, I seem to remember. At least it wasn't a bear. That's the main thing. Never stand between a bear and your lunch. Not a good idea. Especially if you're in a restricted area where you can't move backwards. So if you're between a bear and your lunch and you can't move backwards, you're in trouble. The recommended way of dealing with a bear in that situation, and I know it sounds completely crazy, but if you can't get away and you can't run away, because a bear will run twice as fast as you, can't climb a tree, it will run up a tree twice as fast as you easily. The recommended behavior, believe it or not, and it was explained to me, is to stand up as large as you can with your hands held wide, but don't roar, just make yourself big. Because basically bears are scared and they don't have very good eyesight. So there you go. Right, let's move on. So classification models are categorical, meaning they can be used for labeling inputs or decision making. Self-driving car uses classification to decide whether to turn left or right at a fork in the road. Classification model is different from classical regression models, where outputs are continuous, such as the size of a shoe or the speed of a train. Classification models are diverse in how they work. To get started, we'll focus on logistic regression, which is a simpler and popular type of model that is used extensively across many arms of science and industry. Good. Predicting avalanches. Somebody I know works for the Spanish government, and they predict forest fires using similar techniques, a little bit more advanced perhaps, but similar. Through this module, we'll be using the following example scenario, explaining concepts related to classification. This scenario is designed to provide an example how you might meet these concepts while programming yourself. Your charity is responsible for avalanche rescue operations at ski slopes and hiking trails across the northwest of the USA. While the safest option would be to permanently close all trails over the winter, that would mean no sports people would get to enjoy the great outdoors. Your goal is to build a model that can predict whether an individual day is likely to result in an avalanche, so that you can close the trial when the risk is high. Keep in mind that as you make predictions, that predicting avalanches that don't happen can hurt local tourism. Failing to predict avalanches that do happen can result in loss of life. So clearly a balance is to be found. For those eager hikers and skiers out there, machine learning can be used for avalanche prediction, but the data for these exercises are completely fabricated and solely for educational purposes. Please don't use this data or your train model for anything except learning about machine learning. Don't offer it as a service to your local, your resort. Well, I don't know. It's crazy. If you don't put disclaimers on things like this, I mean, I know of cases certainly that people have, and it's a terrible thing, they put their dog in a microwave to dry the fur, and of course the dog just explodes. And people then have sued the microwave company because it said not to do that. It didn't say in the instructions not to do that. There is no common sense in no. I mean, for example, again, just on microwaves, people were not told that they couldn't open the door and you put their full weight on the door in order to be able to reach up to a higher cupboard. And the door smashed off and they sued the company. It's crazy what you have to do. I mean, for example, a friend of mine works in vending machines all over the world, and they had a problem in that the cups that they bought, and they buy them by the tens of millions, when they first bought them, people used to have tea. But then they used to sell lemon tea, which was a powder and didn't have any acid in it. But when people put their own lemon in the black tea, it melted the cup and they got scalded. So, and they were sued right, left, and centre. So you've always got to put disclaimers in everywhere. So in this module, you'll discover how classification differs from classical regression. So that's in terms of things being put into categories rather than predicting a value for something. Build models that can perform these tasks and explore how to access and improve them. Okay, so here goes. Classification models are used to make decisions. I'll let you read that. Yeah. Okay. So what we're talking about here, the differences between regression and logistic regression. One, the regression produces a line, logistic regression produces a curve, and you can then simply say what happens if something is above the curve or below the curve, because the probability can then be expressed as a number. And then you can simply apply a simple mask that says if it's more than here, as we've done here, if it's more than 0.5, which is this region here, then it will be a positive thing, and if it's down here, it will be a negative thing, or true, or false, or whatever you want it to do. It's a binary decision. about where you can then say something is. So if you're in here or in here, you're going to get a different output of your classifier than if you're there or there. That's what this does. So gives the these probabilities rather than a simple true false. We need to convert that into a true false using some kind of limit or threshold. That means that any value, any y value between 0.5 is converted to false, left bottom box, and any value above 0.5 is converted to true, above right box, that one there. So looking at the graph, we can see this means that when a feature is below 5, the probability will be less than 0.5, and so can be converted to false. Feature values above 5 give probability above 0.5, and so will be converted to true. So this is our feature value. Here. And depending what range you're in, you assign it a different probability, and then the probability is indicative of either true or false, yes or no, whatever it is you want to look for. So it's notable that logistic regression doesn't have to be limited to true false. It can also be used where there are 3 or more potential outcomes, such as rain, snow, or sun. This requires a slightly more complex setup called a multinomial logistic regression. While we won't practice this during the next few exercises, it's well worth considering in situations where you need to make predictions that aren't binary. So we're going to build a simple binary logistic regression model. Have I still got my sandbox? Yes. Good, good, good. Now I have to activate a new one. Okay. Let's have a look at this. We're loading in something called stats models we had before. And we're loading in our data, or graphing.py, which is our nice Plotly wrapper, and our avalanche.csv file, which is a made-up file. And we're going to simply put it into the data set. It's just a pandas read.csv, so we're going to read that CSV file into the panda array called dataset using a tab delimiter. So let's have a look at the dataset. Just type it in here, and we'll get the first 5 rows or so. Okay, there's our data set. Down a bit further. Then a bit further than that. And here it is. So top and tail then of, or head and tail of our data set. We've got an unnamed column here. We've got 1094, so I would say this is some kind of index. Yeah. Whether or not an avalanche happened, so this is going to be effectively our y values, our predicted values. Our class value is 0 or 1 if an avalanche happened. Number of visitors, surface, that might mean, I don't know what that means. Fresh thickness, so how fresh thickness of snow that would be, I would think. The wind, weak layers, and tracked out. Well, I'm sure there'll be an explanation for those terms. Determining weak layers of snow, probably how many short snow showers there's been that haven't consolidated in some way. They're just laying one on top of another, that kind of thing. and are more likely to shear, I would guess. But let's have a look. So we'll look at our data. So we've got 1,095 rows and 8 columns. The avalanche field is our target. The value of 1 means an avalanche did occur, and 0 means it didn't. Since our targets can be 1, 0, or 1, we call this a binary classification model. Let's plot the relationships between each feature and the target values. That helps understand which features are more likely to influence the results. So we're doing a box and whisker on avalanche against each of the other contributory fields. And here we go. So we've got, just looking at the surface, whatever that is not that great. We've got some outliers here. Looking at the fresh thickness of snow, that looks like a very, very reliable indicator. And the number of layers, that's a bit tougher. Yeah, not quite as good. And then the number of visitors, yeah. More visitors will get you more. That's interesting. More visitors will get you an avalanche. Not quite. Will get you less of a chance of an avalanche. The median value is lower. It's interesting data. So for fresh thickness, the outcomes are very similar. This means that variations in their values aren't strongly correlated with the results. So let's go back. So for fresh thickness, go back up. You see that you get the same of everything, whether it's 0 or 1. So that means that that feature is not indicative. Okay? Fresh thickness is not indicative. It has similar ranges, similar medians, so on. So it's very hard to tell the difference between a 0 and a 1, whether or not there was an avalanche and an avalanche, just looking at fresh thickness. So it's less important. A number of weak layers, yeah, that's fairly indicative there because there's a difference here. So for example, if you said to myself, right, I'm going to put a margin on here of what was the difference between an avalanche and not an avalanche, if you put that to be here, weak layers is there. So you could set a value probably around here, around 5. If you set the value for 5, then you would exclude, you'd be positively predicting all of that and negatively predicting all of that. The only confusion area, the only overlap area is these area, this area here where both this and this exist. So you would get a certain probability a wrong result outside that range. So your confidence decreases as you hit the boundary, which is what you would expect intuitively to happen. So variations in values for weak layers and no visitors seems to correlate with a large number of avalanche results, and thus we should assign more importance to these features. So let's have a look if we can interpret that. Well, the range is this kind of same, whether or not you get the avalanche or not, but the median value here is different between 4 and 5. Yeah, you get quite a large range you can use. So the differences between the avalanche and non-avalanche days are small, and therefore there isn't one clear driver of issues. Weak layers looks like a good starting point, and it is related to the widest variation of results between 0 and 1. The others seem to be a bit close. I'm a bit surprised visitors wasn't a bit more pronounced than that. Building a simple logistic regression model. So we'll now build and train a model to predict the chance of an avalanche happening based solely on the number of weak layers of snow. So really, that's almost like a regression. Let's try. So he'll import a function that splits the data sets. Yeah, we know about all that. Train test, it's train test of split data. Yes, we've done that. And we just do that. We're just looking at just to check that our train and test is split correctly. 76 by 8 and 329 by 8 makes sense on a ratio of 70-30. So we're all there. So we're looking at our model using the train data set. So we're graphing. That's because we're going to do some plotting here. We're going to use SMF as our stats model formula and perform our logistic regression. So model is SMF of logistic regression, so log it. And our key explanation here is how avalanche is explained by weak layers. So now create a model on that basis. That's what we're going to do now. So it terminated correctly. Correct function value is 0.6 and the iteration is filed. The model's trained. Let's print it. Model summary. Here's our model summary. So dependent variable is avalanche. That's the thing that depends on the experiment. The model is logistic regression. And it did converge. Okay. And our numbers for it are here. So notice that the positive coefficients for weak layers means that higher values mean a higher likelihood for an avalanche. This is a weak layer and it's positive. Okay, we're going to use the model. We can use our train model to make a prediction and estimate some probabilities. Let's pick the first 4 occurrences in our test set and print probability of an avalanche for each of them. Okay, so get the first 3 samples. So samples test weak data 4. So that means everything up to 4. Use the model to get predictions as possibilities. Estimated probabilities is our model prediction based on our samples, which are these, our first 3 samples from our data set, and print the results. That's what this is doing. And here we go. So a weak layer with a value of 5 yields a 56% chance. 4, 59, 7. Yeah, so if you've got lots of weak layers of snow, then you stand a good chance of getting an avalanche. So that is a good indicator. Now what you've got to do is to then put a limit, never mind the probabilities, but is it going to happen? Do you think it's going to happen? So let's plot our model. See everything? There it is. There's our logistic regression model, purely for so the line plot's a function of the probability of an avalanche, estimated probability of an avalanche there, over the number of weak layers. Note that there is more weak layers, the more likely an avalanche will begin. This plot can look a bit confusing for two reasons. Firstly, the curve can make predictions from negative to positive to infinity, but we only have 0 to 10 layers. Yeah, we can't really have minus 10 layers. So all it's saying is that it will be symmetrical. About there. So, second. But we have only data for 0 to 10. So print minimum number of weak layers, minimum train, maximum train. Let's have a look. So minimum number of weak layers 0, maximum is 10. That's in our training set. They allow predictions outside the range they've seen. That's often not so good. Second reason the plot is confusing, in that 0 layers, there's still some risk of an avalanche. Similarly, at 10 layers, there isn't 100% risk of an avalanche. This is actually in line with the data. So get the actual values at 0 years and get the initial rates of avalanches at 10 years. And the average rate for avalanches for 0 week of snow is that. So it's not 0. Okay? The rate of avalanches for 0 week layers is not 0. The average rate of avalanches for 10 layers is not 1. Somewhere in between. So our model is actually doing a good job. It's just that the avalanches aren't only caused by weak layers of snow. If we want to do better, we need to think about including other information in the model. Yeah, so that is a good indication. It's called boundary testing. Whenever you do anything, the first thing when I'm coming up with a new formula or a new equation or a new way of doing something, I immediately test it with the boundary values, and which are the extreme values. And if the extreme values look sensible, if it can work well with the extreme values, then it's likely to work quite well in between. If the extreme values produce infinities or a whole line of zeros, then no, it's not going to generalize very well at all. So you try and do that. And of course, in doing that, you can actually extract from that your rescaling parameters. Because if you know what the minimum value of your function is, based on the minimum value of data that it's ever going to see, and the same thing with the maximum value, you've now got your limits where you can rescale your parameter. So it's a very powerful idea. So our model is doing a good job yet. So classification or decision thresholds. To return a binary category, true avalanche, false avalanche, we need to define a margin, a threshold value. Any probability above that threshold is returned as positive, whereas values below will be returned as negative. Let's see what happens if we set our threshold at 0.5. That makes sense. So here we go. We set this here as threshold equals 0.5. for sample dot. Okay, so this is all of the ones that's in this list. Apply the threshold, basically. So a weak layer with value 5, nil to 50% chance, classification, true. True, false, false. So that's simply applying that threshold there. Let's carry on over here so we can see. Yeah, there's the business end of it. We're passing this parameter, prediction greater than threshold. If the prediction is greater than the threshold, then that will come out to be true or false, because that in here is a test, a Boolean test. If basically whenever prediction is greater than threshold. So for each of the samples, we say whether or not the prediction is greater than the threshold. I've got something in my head that's not good, because what happens when they're the same? Now, when the prediction equals the threshold, does it not print the value? So it's a bit sloppy, really. You need to have maybe a greater than and equal one, because otherwise sometimes you won't get a classification. Yeah, if they're exactly equal to each other, then prediction is not greater than, and so it's not a Boolean. It would struggle. That's why you normally put this in. You normally put in what works is usually I can get in there. That greater than equal to. Sorry, equal to or greater than. I think that's allowed. Did I put an equal sign in there? Yeah. Or is it the other way around? You put the equal sign afterwards. I think I don't. Let's have a look, see if it prefers that. It didn't like what I did there. But so greater than equal to. Yeah, that's better. So let's try that. Probably won't make any difference. We've got our first 4. Yeah, it's made no difference here. No, because there isn't a sample there that's equals. But I think it's a better function anyway. Okay.
We might have to close the double quotes to get, if we are trying to execute something, so we might have to close the double quotes before that.
Ah, I see what you mean. No, I'm just putting in a different test. I'm making the test greater than or equal to.
Yeah, so the double quotes which is after curly braces should actually come before.
Ah.
Yeah, so we have just in the end there's a double quotes. Yeah.
Classifications equals predicted.
Yeah. So so this double quotes, if we shift to before curly braces, there's a double quotes.
Ah, it should be there. Well, no, because that puts us inside the parameter. This is a.
No,
this
that's
is basically
fine.
A result, isn't it? This will return true or false. Yeah,
so we will close the double quotes there and then put a dot in between. So dot will concatenate 2 things.
And how's that going to change what we've got down here?
So we want to print the result of that, isn't it? The predict is greater than threshold or not.
Yeah, we've got that. True, 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 false. That's this bit here, I think. Yeah, binary is returned.
So that is,
I think I know what you're getting at, but this here, these curly brackets, means whatever result this comes back with, that's what you're substituting in.
Yeah, actually, you're right. Yeah, because
so
we
this is
do
like
this
a
formatting.
function.
Yeah,
This is
that's
like
true.
a parameter,
Yeah, yeah,
and so the quotes are outside that. It
yeah.
doesn't matter, but yeah. Okay, so notice 0.5 is just a starting point that needs to be tuned depending on the data we're classifying. So let's check our performance. What do we always do here? Well, we're going to look here for accuracy is the NumPy average predictions equals the test avalanche. So basically, it's simply saying what is the average number of predictions equal to the test avalanche. So that takes away, it works out that we've got 4 samples and then calculates the average correct predictions against the test. And we end up, the model accurately predicts outcomes at 65% of the time, which is not great. Bear in mind that tossing a coin will predict the outcome 50% of the time. And this is this rock curve that we looked at before, where we're looking about your prediction compared to tossing a coin. Yeah, we only use the weak layers, so we really need to we need to bring in other factors, don't we? So let's have a look. So avalanche is hard to pick, but we're doing okay. It's hard to tell exactly what kind of mistakes our model is making, though. So we'll focus on this in the next exercise. In this unit, we covered the following topics: using data exploration to understand features that have a stronger correlation to the outcomes. And that's what we did with the box and whisker. We could see we were looking for a big box and whisker variation between our 0 and 1. We can see that that is a discriminating feature. That's what we're interested in. And we would regard that as signal rather than noise in what that guy was talking about before. Building a simple logistic regression model using the train model to predict some probabilities, using thresholds to map the probabilities to binary classes, and how to use test set to measure the model's performance. Well, that was just a simple averaging there. So let's assess our classification model. I'll give you a chance to read that. We probably won't be able to get onto much of this, but have a look on those. So yeah, we use log loss because it punishes outliers. results that you predict that are incorrect. Okay, so tomorrow we'll start by assessing our logistic regression model. Let's move forward to where we are. And this is where we'll begin tomorrow. I'm going to visualize it, fit it. So we're going to do accuracy predictions, measurements. And this is where NumPy really comes into its own. And that's where we'll begin tomorrow. So now we're looking actually pretty close to what real data science is about. The models that we looked at today are not Mickey Mouse approaches. They are pretty close to becoming what you might call state of the art in terms of these particular problems. If you've got a very large number of values, then almost certainly a neural network approach is the way to go. A deep learning approach is generally better. Although random forests are seen to be very, very good classifiers. So we're not too far off what people are actually doing day in, day out. And a lot of the research papers mention pretty much all of these terms if you spend any time with them. So yeah, what we're doing is quite realistic. So I will see you all tomorrow, hopefully, and we'll move on to assessing our regression model. Okay, so cheerio.
Thank you. Bye.
Thank you. Bye.